So thinking back to when we were looking at a car going around a curve, like this instance, we know that there's some acceleration acting towards the center of the curve, which is our centripetal acceleration. And here's our force diagram for the situation. And so that centripetal acceleration we learned was generated by the static friction on the tires. So when you turn the wheel, it creates some friction against the line of movement, which causes a change in direction. But now we want to talk a little bit about banking, because a lot of times in cars, if you pay attention on the freeway, they actually bank the road as you enter curves. And there's a reason that they do this. So first, let's just look. So here's an object, a car going around a curve, and it's going about 60 miles per hour, 27 meters per second. And if we increase the velocity, what you should notice down here is the static frictional force is increasing. And remember that there's a maximum that can be reached that's determined by the coefficient. The average coefficient is about 0.7 for a car tire on the road. So if we increase that velocity, you see how it turned red there? So what's happened is we've exceeded the frictional force that can be applied on the tires by the road. And so the car at this point would then go off. We no longer have some centripetal acceleration. So the car would go off the road, basically. And you see this if you, like on the spaghetti bowl or any big on-ramps, look at all the scrapes on the side. And what happens there is the cars are going too fast. And so they've exceeded the static frictional force. So they continue in a straight line. And that's what the barrier is there for. And this can happen at a slower speed if, say, your tires aren't brand new. And so you've lost some of the friction. You can see down around 0.25, that's it. You've exceeded the maximum frictional force, static friction, and so boom, right into the wall. So depending on, let's see, how fast could you be going around this? About 50. So you'd have to slow down to about 50 miles an hour in order to make it around the curve. Now, engineers, what they do is they bank the curve. So let's put this back to about 0.7, and let's say we have we're going 60, whatever, right around 60 miles an hour. So what they can do is they can actually bank the curve, and look what happens to the friction as they start increasing the bank. You can get it to the point where it actually disappears. And that's around 15 degrees. So the question then was, well, what's causing it to turn? You can see that it's clearly turning, and that comes from the normal force. So you can see now we have a component of the normal force acting in, and this is acting to create our entire centripetal force. And if we increase it further, you'll see that the normal just starts increasing, but now we have friction going in the opposite direction. That's preventing you from sliding down. So again, same kind of situation. What happens if the coefficient of friction decreases? You can see now, no matter how fast you're going, you're going to slide down the road. So this would happen on an icy road. So what you would want to do is actually increase your velocity, and now you can make it, even with a lower coefficient. It's interesting, huh? So actually on a banked road, if you have icy conditions, you don't want to go slow. You want to go at the recommended speed, and you'll make it around regardless. Even if it was a coefficient of 0, you could still make it around if your velocity was great enough. Now, I'm not going to be able to show it here. But if you had Teflon tires on an icy road and it was banked at the proper angle, you could still make it around the curve. So why are we talking about all this? Well, you want to be able to analyze the situation with friction and without friction. And basically, if you can find, when friction is not a force, you found the optimal speed to go around a banked curve. Highways, typically about 14 degrees. That's about what they'll do on a bank. So if I set it at 14 degrees, coefficients there, I can see that it's safe up to about 100 miles an hour. And I can see that the design speed, where friction doesn't matter, is right around 60 miles per hour. Interesting. If I lower that, You go to an exit ramp, you're probably looking at maybe 10 degrees. Then I can see that my design speed is down around 45. So when you're getting off the freeway and it's a banked curve, pay attention to the speed limit. The speed limit will be the optimal so that you don't feel any frictional force. So what I like to do now is I'm going to work through an example and say, if this is 10 degrees, what's that velocity? What's that optimal velocity? In other words, the design speed. So if we have a 10 degree bank and the mass of my car is about 1578, or is 1578, the car and driver and everything in it, and the radius of the turn is 200 meters, what's the optimal velocity or the design speed of this? In other words, we don't want any friction involved. So our centripetal force comes strictly from the normal. So let's break this out and draw a force diagram. So I'll draw it kind of big to try to, I know this isn't 10 degrees, but we're just trying to get a picture going. Okay, so there's my car. We know this is 10 degrees. So since we have an angle, we're going to be using some trig. And let's go ahead and define our x and y. Now notice what I'm doing. Since my picture is drawn this way, I'm going to define positive x to be in this direction and positive y to be in this direction. So x is coming to the left now, positive x. Now let's draw some components on here of our forces. So we have weight, and then we have normal. Oh, that's terrible. Let's try to get it perpendicular. Okay, there's my normal force. So you have to not get confused with an inclined plane problem. That's not what this is. We're just analyzing the motion from the back of the car. We're looking like towards the back of the car as it's moving around in a circle like that. It's going to curve kind of into the screen, like that. It's following this path. So we're trying to figure out the force that's being applied so that we can determine the velocity and so forth. So our axes are different. They don't go down the plane. This car, we don't want it sliding this way. We want it's moving, no movement in this direction. It's all moving forward along the curve. So we're not going to draw our triangle down here with the weight. That wouldn't help us. The weight is already in the y direction. We're going to break out this normal. So we do it in it's similar way, is we have this piece, which is my normal in the y direction, and then we're going to have a piece over here, which is the normal in the x direction. And it's this normal in the x direction that's my centripetal force. This is the only force acting. Now, if I had friction, I would have some components of that's adding to it. But in this case, we're trying to find the optimal, so we don't care about friction. So now we can start working with it and try to figure some stuff out. I don't know what the normal is. The normal is not in direct opposition to the weight. However, the normal in the y is. And we know that the car is not moving up and down. So we can say that the sum of the forces in the y direction would be equal to the mass times the acceleration in the y, but the acceleration in the y is 0, so the sum of the forces in the y is equal to 0. So my forces in the y are my normal in the y direction plus the weight, and that's all equal to 0. So my normal in the y is equal to the opposite of the weight, and weight is given by mg, so we get negative mg. Weight is down, so the g is negative. So we get the normal in the y is equal to the opposite of 1578, my mass, times negative 9.8. And we'll take the negative of all of that. You get the normal in the y direction is going to be 15,464.4 newtons. So that's the normal in the y direction. Now with that, I can find the normal in the x. Now this angle here goes right here. So 10 degrees. So I need to find my normal in the x. I don't care what the actual normal is for this problem. What I care about is this normal in the x, because with that, then I can determine the centripetal acceleration or the velocity. So I see that my normal in the x, just draw a line, that it's I need the opposite, and I have the adjacent, so that's tangent. So the tangent of 10 degrees is going to be the opposite nx, the normal in the x direction, over the normal in the y direction. So I just multiply. So I get the normal in the x direction is going to be the normal in the y direction times tangent 10 degrees. And calculating that, we get the normal in the x direction is 26.79. I'm rounding here, but in my calculations, I use the entire number. Okay, so now we have the normal in the x. So now we can move from the sum of the forces in the y to the sum of the forces in the x, and we can use all this information. So the sum of the forces in the x direction is going to be the mass times, this is centripetal, so we have a centripetal acceleration. The sum of the force in the x, the only force in that direction is the normal in the x direction, and that would be mass times, and now I go ahead and substitute my equation, remembering that the centripetal acceleration is going to be v squared over r. So we get v squared over r. I need to solve for v, so I'm going to divide by m and multiply by r. So I get r times nx divided by m equals v, but that's v squared. To get rid of that, I just take the square root on the other side. So this equation will tell me the optimal velocity on this curve. Plugging the numbers, the radius was 200, the nx is here, the mass is 15. We get a velocity of 18.59 meters per second. So that's our optimal design, or our design speed would be 18.59. That's about 41.58 miles per hour. Yeah, and that's it. So this is optimal design speed. If we had friction, we would do the trig on it to get our frictional force in the x. And it depends on how fast you're going, really. Sometimes the friction is acting down the ramps or down the banked curve or up the banked curve. It just depends. So you just work with what you have, use your trig. That should be it.